and also share some of my perspective of like my goal and my program, and try to use Gemflip to understanding basically our chemical origins in our Earth. So before I talk about that, it's actually an event. It's much recent compared to the launch of Gemflip. There's a lunar eclipse tonight. It is an almost total lunar eclipse happening tonight. So the peak is about 3:03 3 a.m. After midnight. So if you stay up pretty late or you wake up really early, this is a really good chance to see a lunar eclipse. You can see that the shadow of Earth just block almost entirely of the moon, just like tiny little pieces outside. So you probably will see a very interesting contrast if you happen to be around outside or awake at around 3 in the morning. All right, so back to Gemflip. So to me, like I study how the stars form, how the planets form, and one of the driving force or motivation to understanding all of these, like driven my science basically, is to understand how does life occur on Earth, like how does life actually begin? Like we all, to like a biologist, to probably say, okay, you just have this kind of evolution going on. You're starting from this very primitive organics and evolve into like dinosaurs, eventually to humans. And going back to the kind of, if we rewind the time a little bit, we can kind of trace all of this life into like organic matter. And you starting with some few molecules, and given time, evolve into all kinds of different organisms, and eventually like you can like evolve into like my dogs in Taiwan. It's pretty cute. So we really want to like look into how do we get here? What's our chemical heritage basically? What's the chemical evolution leading to this point right now on Earth when I can talk over Zoom to you guys? So one place that scientists have been looking into is comet. So comet, as we know, it comes and goes very rarely. Once it's tens of years, and or even just like fly by and not even coming back. Therefore, this comet actually spent a long time of their lifetime in very outside of our solar system in very cold environment. Therefore, the material on the comet get a very little alteration or so-called thermal processing. They have very little effect from the sun throughout its lifetime. So we think this is the place we can find the pristine material on those comets, and it will help us to understand what are the chemical composition in early times during the formation of our solar system. So this is a Rosetta mission. This is satellites and flew to see comet 67P. I think maybe 5 years ago, even more than that. They take a lot of spectrum of this source, and actually detected basically a soup of various different kind of organic molecules and very early stage, and even detect like simple sugar, like very simple protein. So it just showed that the chemistry actually evolved pretty early on in terms of the formation of our sun or our solar system. And to date it back a little bit, all of the other observation evidence suggests that the star's journey is really starting from this cold, dusty cloud, which is like the black spot you see here. This is a visible, like camera-taken image of Perseus molecular clouds. All of these dark spots, dark patches, is where you have a lot of dust. It's more like going out in very cloudy, almost like raining days. You couldn't really see the sun. It's basically what happened here. So we couldn't really see the starlight behind it. And that's where things are cold and dusty. That's where you have a lot of material from in a very dense environment, and that's where that's exactly what is the nursery of a newly born star. And so we're interested to look into in those regions to see what are the chemistry markup for those regions, and to see how is that compared to our solar system, to the comet, which is the early stage of our solar system. And so people have been looking into those kind of things. So this is one of a very like a poster child sources, and this is we call Protostar, but it's just basically a baby star, a star that just born. So still have a lot of material around it, and over time the star will grow by just accreting those material and kind of grow in mass. So with radio telescope like ALMA shown here, so it's managed by, like, for example, the National Radio Astronomy Observatory here in Charlottesville. We take a spectrum of that and actually see a lot of these like kind of like peaks in the spectrum. So each of these peaks is a signal for molecules, and so you can see that you can barely pick out any flat region, suggesting that there's just like tons of different molecules in here, all kinds of different molecules. There are methanol, there are ethanol, which is like alcohol that we have in our beer, in our wines. There's all kinds of organic matters that we interact every day, and it already exists in the like very, very early stage when the star just formed. So it's very intriguing, like how does this rich chemistry come in at the very beginnings. So if we go further back to see, like, okay, how do we see these molecules in there in a gas, like molecular gas, and we use our radio telescope to see it, and we actually realized that ice is where actually all the fun things reaction begin. So let me show you how it's work. So imagine you have a cloud of gas, cloud of molecules. In the center, there could be a stars forming. They give out radiation just like our sun. If you're closer to our sun, it's hotter. If there's a further away, it's colder. So center is redder, which in my visualization is hotter. So if we zoom in, we'll have like star in the center. The outside is much, much colder. And what happened in cold environments is that things get icy, right? When you go out in the very snowy days, the floor get icy, you have a thin coat of ice. And that's exactly what happened in those regions. In those, like I said, very dusty cloud, those dust is like the soot you have in your fire pit. And over time, we start accumulating atoms like hydrogen atoms, oxygen atoms, and they just stick onto the surface of this dust grains. And over time, to form basically a thin coated or various different layers of ice, like could be water ice, could be carbon monoxide ice, and just like have this like ice mantle on top of these dust grain. And that's actually where a lot of things could happen. On that dust grain, if I kind of draw in a kind of like a cartoonish picture here, you have a dust grain, you have a coated of ice. On those ice, like these molecules, like or smaller molecules, can kind of react to form the larger molecules because they can just like reside there. They don't fly around. They kind of like grounded to certain places. So there's much better chance that can react with each other, form a larger molecule that kind of facilitate the growth of a complexes of molecules. And once this icy grain like going to like fall, like because the gravity pulls it to the inner part, the star is growing, the temperature rises, and therefore this ice will sublimate. Like the ice just gone, become like part of the gas, and these molecules just become the gas phase, and that's where we see those molecules with our radio telescope. So a lot of reactions is actually happening on this ice mantle, which is basically invisible from our radio observation, from our optical observation from our eyes. And this is a tricky problem because we know a lot of things happening in our eyes, and that can driven the chemical evolution that we see, and we see the outcome of that, but we don't really see how it actually happens. So how are we gonna see this ice? Another way we can see this ice, like remember, is like we have this, for example, this is a water molecules, because they have very little movement on the dust grain because they are frozen. We don't really typically see their emission. Instead, they have this kind of vibration mode. If you just like give it a little bit of energy, it will like vibrate a little bit. And therefore, we can use this characteristic as a way to detect those molecules, detect or kind of analyze what's this composition of this ice on the dust grain. The way to do that is that you have, for example, a starlight, some background source behind those icy grain here, and we're observing from the other end. And we have radiation coming in. Some part of radiation get absorbed or like turn into the vibrational energy of these water molecules. And therefore, in the end, we just see a similar spectrum, but missing some part of the energy, some part of a spectrum. Some like we're just like, oh, this star should look like this, but something's missing. And from the missing part, we can really figure out like what's the intervening IC the screen that caused these kind of specific features, and that will help us to understand what kind of species is on the screen. So in the end, we could have these kind of spectrum where here is just basically how energy is distributed at different wavelengths. So if there's no intervening ice, we probably would have more like a flat lines or something like that. But now we actually see a lot of like dips, and that means that there's energy missing in specific wavelengths and specific energy, and we can relate it to certain molecules. Like here, we can relate it to carbon monoxide, methanol, carbon dioxide, and that's a way we can use spectrum and also absorption spectrum to figure out what's the ice composition on those grains. And one tricky thing is most of these signature, as in they're really faint, and those sources are really faint because remember they're embedding those cold, dusty cloud that we can really not even see it with our camera. And most of these features are infrared light, which I'll explain a little bit later. And so to really make advancements on these areas, myself included and some other teams actually try to use the newly soon to be launched James Webb telescope to look into this problem, because the unprecedented sensitivity and resolution that James Webb Space Telescope can offer, they'll greatly advance what we had before for getting those kind of observational signature. Previously, we can only do it for really bright source, and even for those sources, we have to spend quite a bit of time. And now with James Webb Space Telescope, we can do a lot more sources and has much higher resolution than we previously could. So now I'm going to pivot a little bit to give you guys some introduction about what the James Webb Space Telescope is. I think in the past few decades, we have been launching telescope in the space. And one of the driving force is like our Earth's atmosphere is actually quite messy or opaque. Like you see clouds come and goes. The Earth's atmosphere actually absorb a lot of like UV lights, and also absorb a lot of like infrared light. So you don't really get a really transparent window from the Earth. It can be transparent if you're just like looking at with our eyes, but with various different telescopes, they really need to be put out of space so that we can take advantage of unperturbed like surrounding environments, unperturbed. There's no atmosphere out there, but unperturbed conditions. And in the past few decades, there's Hubble, Chandra, Spitzer, they all focus on from ultraviolet, visible, infrared, and X-ray emission. And those telescopes has made great progress into the advancements of astronomical discoveries. For example, that we know with X-ray, we can see the dying star, the remnant left over from the explosion of the dying star, which is a Crab Nebula. With infrared light, we can understand why it does look like this like funny curved shape. That's because there's a star behind it. We can actually see it with infrared light and to see how it is affecting its surrounding material. And we can also, this is a Hubble image, a ring nebula, which is various different gases that putting out by a dying star as well. And with all of these observatory combined together, we can actually have very gorgeous combined like image of like this is antenna galaxies, but then each different color is going to highlight different parts of the gas, or maybe in high energy regions or hot or cold regions. So combining all of these telescopes actually give us a lot more information about a single telescope, and also they are far beyond anything we can have from the ground. So I mentioned about infrared lights. Why we care about infrared light? Why not just look at that and we can say, oh, okay, this is red, this is blue, this is green. So before we talk about that, let's just like focus on what is infrared light by itself. Like, so this is like electromagnetic spectrum. So our visible wavelengths actually like tiny little bit on this entire spectrum. So that's the visible just means where we can see. With Hubble Space Telescope, we can see a little bit more than the red. We can also see a little bit more than the blue. And with James Webb Space Telescope, we can see a lot redder than the red we can see. So if the light become more red than the red, our human eye is not very sensitive to that part of it, radiation. But we can build an instrument like JWST to pick up those emissions. And those are the emissions that can give us a different perspective of what the object might look like. So here's one example. So here's 3 little meerkats that are curiously looking around, and there's a crocodile image, and they're just what we see in invisible light. That's just how it will look like from our naked eye. But with infrared light, you can see they look very, very different. So meerkat, maybe they have a lot of fur, so they actually become brighter because they have a higher temperature. And this crocodile maybe just coming out from the river, it actually has a much colder temperature compared to the surrounding its surrounding. And you can also see the infrared lights also pick up a lot more detail in the background. Like for example, these dark patches right behind these meerkats. You can see there's some structure there, maybe not entirely clear, but you definitely see more than just a pitch black as you can see in the visible light. So in astronomical regions, James Webb also will allow us to peer through a kind of intervening material and see kind of like what's behind it. So in the visible light, this is a Hubble image. We see this is the famous image of Pillar of Creations. You see a lot of the clouds here, and you kind of don't see anything behind, right? As we switch to near infrared light, which is just slightly redder than the red, we start to see a lot more structure. Start to see a lot of structure behind that. And on the far right, this is a mid-infrared light taken by Spitzer. And now you can see all of these the structure that were dark in visible light become bright instead here. So we can kind of analyze what are those structures look like, what's the thing behind that. And this is with a smaller telescope that we launched before. With James Webb, we'll be able to reach about the same resolution as the Hubble, which the one on the tube image on the left, and at this particular wavelength. So we'll be able to basically sharpen up this image and kind of really understanding the interplay between dust and gas and how it makes star, how the star is dying, how it's affecting its surrounding materials. So there's a lot of science cases that scientists are preparing to use Webb to explore. I'm just going to show you a few highlights in this talk, but there are a lot more that people have figured out a creative way to do their observations. One of the really sort of a new area in the recent years is exploring the early universe. So the theory is that right after Big Bang, a lot of the gas are really, really opaque. We couldn't really see through those opaque gas at just the beginning of our universe. And over time, stars start forming and heating up the gas surrounding, kind of clear out those opaque gas, and therefore evolve into a clear universe that we can see. And this kind of opaque region or transitional period time is what we call epochal ionization. So with James Webb, we will be able to look at this particular stage because we can use infrared light. And the reason why infrared light is so important to explore early universe is that the radiation from the early universe, after they travel great distance, it actually become redder. And basically the wavelength, the radiation gets stretching out over time. And so when it emits, it could be very blue, and over time just become redder and redder and redder, and kind of fall into this infrared range where James Webb is specialized to observe. So because of that, we'll be able to see some of the very first galaxies. So this is an image for Hubble. This is Hubble trying really, really hard, and so far we'll find this kind of tiny smudge of galaxy, which is this has been been confirmed to be like about 13.4 billion years ago, which is only 4 million years young after the Big Bang. But with Gemflip, we'll be able to make more and more, like a lot more discovery of these kind of galaxies in early stage, like right at the end of reionization. And we'll be able to kind of get a whole lot of sample of these galaxies and put together and measuring how old they are for each galaxy, and kind of put together like a galaxy flick book. So you can see, oh, this is how a galaxy could form at a different time of its journeys. So we really expect this field going to be kind of like blow up, figure like literally like kind of like booming in the next couple of years once we see a lot of these galaxies being discovered. And another area that we'll be looking forward to have a lot of discovery is really examining how the star form, live, and die. And that's where my research interest is also part of that, is understanding what's the environment of where the star is forming. So here's a Canary nebula with a lot of radiation going around. You see a lot of like arc structures, cloud structures, and you can pick up different structure in the infrared light. And if we can go further into the infrared light, maybe we'll see through all of these still opaque structures we couldn't see through with Hubble. And lastly, we will be able to see a lot more molecules that we'll put in with like previous observatory like Spitzer, Hubble do not have the capability to pick up. And this is exactly where my research program falls in, and to detecting the ice, like I mentioned before. So I'm fortunate to get awards from time and to lead a team with researchers from University of Virginia and elsewhere to kind of look into this kind of spectrum in a few young, just formed stars to really understand how does the chemistry evolve and compare to what we learned from radio telescopes. And we also, I think Susan mentioned in the very beginning, we also will use Gemflip to look into our solar system and see our planet. Believe it or not, we still have a lot more to learn about our planets, the planets that are in our solar system, how does the Jupiter atmosphere changing over time, and so on and so forth. And it will also help us to understanding the planets outside of our solar system. So this is what we see in infrared light and a different time epoch around a I forgot what's this system's name, but you can see there's a lot of tiny little smudges moving around. That's exactly what we see the planets is orbiting around the central star. And with Gemflip, we'll be able to directly characterize each individual exoplanet here to see what's the atmosphere look like? How does it compare? How does it compare to our Earth? How does it compare to atmosphere in our other planets in our solar system? We'll be able to figure out their water contents, carbon dioxide contents, and methanes, etc. So this is because of the Gemflip such unprecedented sensitivities. We'll be able to take a giant leap on characterizing the exoplanet atmospheres. So there's all of the great things that we're going to do with the telescope, and what a telescope, you might be wondering what a telescope may look like. So as you probably seen a few times, or here is another artistic rendition of telescopes. It kind of is like a funny shape. It's not like any telescope will draw a cartoon, or not on any observatory we'll see outside, because it doesn't need a dome. It's just out there in the space. It's pretty empty out here. And how scientists and engineers put together Webb to put together Gemflip telescopes is really a multi-year process with a whole lot of engineering adventures to figure out, for example, what kind of mirror you're going to do in there, how you're going to have this telescope stables, how you're going to kind of pack this really big telescope. You can see how big of this mirror compared to this person here, and just like we're going to pack this telescope into just like 5 meter tall package and to be launched in the rocket. So you're going to figure out how we're going to pack this in the rocket and how you're going to deploy in the end, which I'm going to show you in a few slides later. It's a pretty nerve-wracking process. And the big, like a big improvement that the Webb has done compared to Hubble is how the mirror size is different. So with Hubble, it's about 2.4 meters, and with Hubble primary mirrors, it's just slightly taller than the person. And with Webb, it's about 6 meters across. So because we couldn't really make like a single mirror like that big, I will kind of have to like have this like honeycomb structure where we segmented each individual mirror, so that got to be very careful about calibrating this mirror and have the ability to calibrate it on the fly once the Webb is out here. And it will be a long journey for the Webb to from a launch to where we think where we want it to be. So we put the plan is to put Webb in a position called L2, which is a stable point between the gravity between our sun and the Earth. So the Webb is just going to be orbiting around here, pointing away from the sun, because sun is really, really bright. You don't want your really sensitive instrument pointing to the sun, kind of basically just going to burn everything. And from Earth to L2 is about 1 million miles. So it takes quite a long journey to get there. And she's going orbiting around here, doing observation, making scientific discovery. So on the appearance of the Webb, there's a side of observing, and there's this side of sun-facing side, like I mentioned. So on the observing side, there's a primary mirror. That's the honeycomb structure we see, and the light will come in, reflect on top of this mirror, go into the secondary, and go into this kind of feeds, and all of the instrument it's kind of sit behind and underneath the mirror. And the mirror is separated or like shielded at the bottom with this sun shield. I think there's a 5-layer sun shield. Its sole purpose is blocking the sunlight, blocking the radiation from the sunlight, preventing the telescope being heating up. Remember, infrared light is very sensitive to the heat. We want to make the telescope pretty cold so we can pick up a really faint signal from astronomical objects. So we're going to launch the Webb in a very tiny package like this, and over time it's going to expand. I'm going to expand its mirror, expand its sun shields, put out its secondary mirrors and both sides of the mirror, and unfold it. So there's a lot more moving parts in the telescope, and in a space mission, more moving part, meaning there's a thinner margin of error, meaning you have to do a lot more rigorous testing to make sure everything will go into plane. So as a user of Gemflip, or as a future user of Gemflip, this kind of process really nervous me. I think after the launch, I'll be kind of like unease for maybe a few months, until we are sure that Gemflip is function as it's supposed to do. And this is not just a United States effort. It's actually an international collaboration from scientists all across the United States, and some places in Canada, and also European space agencies. And basically, it's a global international collaboration. So we have researchers from different continents, different countries, all try to use Webb to learn, to make scientific adventures. And so Webb will be launched by European space agencies from French Guiana. And this is the picture when I really like the picture is like they're shipping it away from the boat, and there's just a person taking a picture of that and saying goodbye to the Webb and kind of ship it over to French Guiana. So the fun fact about the shipping process is that the NASA really has to send out. They're really being like secretive about the route the ship's going to take and which ship's going to be. And they probably, I think they even send out like decoy ships because they want to make sure that it doesn't like face any like attack or something when it's traveling on the oceans for maybe a month or so. This is a several $1 billion investment, several $1 billion instruments. You don't want to either being damaged or fall into wrong hands. So that's kind of like an extra layer of complexity. Like me as a regular person won't even think about that. And needless to say, it has arrived French Guiana, safe and sound. We have this is basically an unboxing picture of Gemflip in French Guianas. Like Susan mentioned before, the launch date is December 18th, 2021, which is about a month from now. And so be sure to tune in to see how launches go, and send good prayers to make sure launch goes smoothly, as smooth as possible. And after we launch, after we go through all of the testings, we're just going to see a lot of science discoveries. It's going to wait. We will see a lot of, like mentioned, we'll look into early universe, seeing those ancient light from the galaxies, and in the epoch realization, we're going to see galaxies over time to piece together basically a life journey of the typical galaxies in different environments. We'll be able to look into the star to see how they're born, what's the environments born. You can see the eyes I'm looking to. We also will see the remnant of a dying star, what's the material is, depending on how it is affecting the nearby environment. Maybe there's a star just right next to it, what happened to those stars. And very excitingly, we'll be able to learn a lot more about other planets, other worlds, maybe just like our Earth. Those planets also have Earth-like atmosphere, or how is it compared to perhaps like Mars and Venus? How well we can characterize their habitabilities, their mass, their gravity, so on and so forth. So all of these we're gonna learn a lot from Gemflip telescopes. So I guess I'm going to stop here and see if you get. That's all of my talk. So thanks a lot for tuning in, and I'm going to stop here and take questions.
Okay, thank you. That was fascinating. I would never have, right, you're right. I never would have thought about the need to have like decoy ships to make sure it gets to where it needs to go safely. It makes sense that we would want those. There was one question early on, so I'm going to see if I understood it correctly. When you were talking about the ice layer and like the dust particles, and you were talking about all the different particles, and they asked, so the different particles turn different colors. So when you're looking at them, they're different colors. So and that's how you can tell what they are?
Okay. So yeah, let me go back to that. So what happened is, if we just observe a star, we may see just a flat signal across different wavelengths, and different molecules will have its characteristic vibrational pattern. Like, for example, water will vibrating in this kind of like wiggly tail fashion. Maybe ammonia its molecular structure is different, so its vibrational modes will be different. Therefore, it will absorb different kinds of energies throughout the electromagnetic spectrum. So for each like individual kind of peak or dips, or trough here, is where scientists can attribute that. So, oh, this is correspond to certain vibrational mode, and therefore it could be these kind of molecules. So we don't necessarily see certain colors. We actually see a missing of certain colors on the spectrum, and that's how we inferred it. Yeah.
Okay. What is the hoped for timeline for operational status? Like how long after its launch will people start being able to use it, or will we see images from it?
Yeah.
Ideally.
So yeah, that's a great question. So I mean, I thought about that a lot because I have some stakes in there. So the official timeline is it will do a lot of testing and also getting their deployments in the first 6 months after launch. So the scientific operation is supposed to begin 6 months after the launch. So will be May, June 2022 next year.
Okay.
And in the very beginning, they actually do, NASA is actually going to do several programs, a so-called early release science program. It's a few years ago, just basically scientists from different fields come together and put out plans like, okay, this is the subject or target that we should test Gemflip telescope upon. Like, make sure we understand how Gemflip telescope works, and using those programs. So those programs will be the first to be executed, and those the data will be released to the public as soon as they're taken. And so I will probably bet on you probably will see some images maybe in the summer of next year. That's my hope.
So there'll be things that we have seen before. So it's a way for them to test to make sure everything's working.
Yeah. Or so like the source, like we kind of know pretty
Okay.
well. Yeah.
So we can see what we know what we're seeing more of.
Yeah.
How much further into space is Webb compared to Hubble?
Oh, I don't have a number for Hubble, but the Hubble, if I remember correctly, it's about a few tenths of a kilometer away from the Earth, compared to the Webb is a million miles, which is almost a million kilometers. And therefore, we can send space shuttle to service Hubble. We cannot send shuttles to service Gemflip. So they really want me to make sure everything goes as planned. I don't think there's a second chance to fix anything. And the reason why it has to be sitting so far away is one, it's a stable point so that Webb just can be there, and also that it is a place it can be really cold. Hubble is not very sensitive to those infrared lights, so it doesn't need to be put in that condition. So it has to be sitting really far away, kind of facing outside from the sun.
Okay. Why was French Guiana chosen for the launch? Do you know?
I actually don't know. I know ESA. That's probably where ESA launched their rocket. The rocket is Ariane 5, so it's, as far as I know, one of the heaviest loaded rockets you can get nowadays. Like Saturn V is no longer used, so they didn't. They need to have something that can carry a heavy payload in the sky. So maybe in the future, if there's other heavy payload rocket, and we can launch from elsewhere. Yeah, but that's the partnership that NASA had with ESA.
So the rocket itself is a European Space Agency. The rocket. Okay.
Yes.
And Webb was built in the United States.
It was built in the United States,
okay.
But several instruments, different parts are built either. I think a Canadian Space Agency contributed to one of the instruments, and some places in Europe, I think, or ESA as in general, also contribute to a few parts of the instruments. The telescope itself was contracted to Northrop Grumman to build the telescopes, and it was testing in Goddard Space Flight Center, which Greenville, Maryland, is not far away from here. And remember, it was like shipped to Houston, NASA Center, to put into like gigantic vacuum chamber for testing, because that's the only place you can find a vacuum chamber that is large enough, can fit the entire scope in there. And then in the end, they shipped to LA for some testing and shipped from LA.
Oh, wow. So it's moved.
A journey.
It's a journey. Let's see. How long of a period of time has it been since the idea for the James Webb Space Telescope was conceived to when it's been developed and implemented?
I don't. Okay, so I think the James Webb is probably, so every 10 years, astronomy community will put out so-called decadal survey to kind of identify important questions, important facilities that will recommend the national agency to pursue. I think the idea of James Webb, or having a large infrared telescope, came up 20 years ago. And I know the development time for James Webb is 17 or 18 years.
Wow.
So it's a multi-decade project. And I mean, there's a lot of technology that we just don't know at the moment. So it takes a lot more time to kind of develop that and put everything together. There's a lot of moving parts. There's animation somewhere in the internet. You can see how it's supposed to be deployed. It's really crazy. Yeah.
About how it's going to unfold and all the pieces. And when do you anticipate being able to get to use the telescope, or do you have a time slot?
Yeah, so I think they have a call for proposal for every scientist to put out their ideas, and there's a selection process to decide which teams get the time. I mean, the data will eventually open to public, but so that first call proposal happening last fall. So that determined the kind of first year of the program is already been set. So all of those programs are being accepted. I'm fortunate to lead one, but there's other researchers doing that. I think the next call will be next winter. So it's going to basically eventually become just once in a year process, and go propose for time and to do that. But the first year's program already been set and have everything queued up. I think the scientists in Gemflip, they're probably pretty busy figuring out where to look at certain things. For my program in particular, I'm expecting to get some data, hopefully in the fall of the next year.
Okay. Can you give us an example of what your team will be measuring with the Webb?
Yeah, so like I said, I was trying to see these kind of features in young stars. So if I can show one of my backup slides, just give me 1 second. So yeah, so this. Oh, so okay. Sir, okay, let's use this. So what we expect to see is, like, for example, if we have like this like blue translucent part is supposed to be visualizing a dusty clouds when there's a star forming in there. So this is from our simulation. We see the inner parts really bright, really warm, and we can see the ice on top of it. So we're gonna use this kind of mesh grid, so-called integral field units in one of the instruments. So basically, you get a spectrum like the one that showed before, has all kinds of absorption features from these tiny little patches. So we'll get basically hundreds of spectrums for like a few hundreds of AU regions, and try to really understanding how this ice composition is varying at different distance and different conditions around this newly formed star.
Okay. Wow. That's a lot of data. It's a lot of data. That's a lot of data to analyze. Yeah. So with the new space telescope, does that mean the older ones go out of commission? Like, will some of them be taken offline, or in Hubble, could we retrieve it and bring it back?
Oh, I don't know if we can retrieve it and take it back.
I don't know either.
So space are already being decommissioned.
Okay.
Because it's just too warm to do kind of condition exceeding what an instrument can operate it. So, but Chandra, which observed X-ray, Hubble, which observed ultraviolet, visible, and infrared, NASA will still operate them as much as they can. There's no termination plan for these telescopes. But I mean, we all know this telescope is old. So I mean, I think a few months ago, Hubble had some issue with computers. They have to switch to its backup computers. There's backup components on those telescopes so they can last long. But then, so recently, there's a decadal survey coming out actually recommend that we should build basically a better Hubble telescope in the next few decades, so that we can actually have like multi-wavelengths access to the space at the same time.
So yeah, so they'll both be there. Is there, we have a question. Is there any plan for a manned mission to L2? Is that possible?
Oh, as far as I know, there's no plan. If you say if it is possible, I think it is possible. But I don't think there's a plan to do so. If things go terribly wrong, maybe we can do that.
So repair, really, how would any repair be done? Is there any repair plan?
No, I don't think so. Maybe someone has no, I don't think so. I think
you may not know that.
Think so. Yeah, I may not know that.
NASA's not sharing that right now.
Yeah.
What field of learning do you feel was most involved in the development of the telescope? For example, astronomy, engineering, etc., or were all fields equally involved in its development?
I don't know. I don't know a whole lot of that engineering process, so I don't really have like a general view about weighting different parts. But I do know like development of infrared detector is quite difficult. Like you have to, and also have very sensitive infrared detector is very difficult process. And so to build Webb and use a lot of infrared detectors, which those detectors can be used to all kinds of different area, both in research facilities or even commercial or industry use. I think those technology can be easily applied to those areas. And also, I guess just I know the sun shield is really challenging for them to figure out. And the tricky thing is that you have to figure out how to fold it back and also take it out without tearing it apart. I think there are like really things that you can think about. It's like aluminum foil, which is like several square foot size, and you have to like expand it, has some tension, and close it back, and without making any scratch. So yeah, I know that's very tough part, and they have did some testing and finally figured it out.
So engineers were very important and astronomers. So everybody was important, and even in pieces we don't necessarily think about. So
yeah.
When the Webb is at L2, is it using power to keep it in orbit?
So they have some thrusters on the telescope, so they can kind of move around, point into different places. I don't think you need a whole lot of power to keep it in orbit, because it's basically like, you can imagine this L2 has some, it's like gravitational center. So if you put Webb in like tiny distance around this gravitational center, it will just kind of orbiting around. And this L2 is really stable. So meaning that it will just orbiting at the same position relative to Earth, at the same position relative to the Sun. So the Earth will move in this direction, L2 will move in this direction, and Webb will just like circling around in this fashion.
So it'll stay in a constant orbit with us.
You will stay in a constant orbit, but it does need some power to kind of like pointing.
So it's solar powered,
Yeah, there's some solar panel. You can see here, right? There's some solar panel, solar power array. They probably have some other mechanism to move a tiny bit around. There's like steering control.
Okay.
Yeah.
But that's all. Steering would come from Earth. Like somebody would send a message to move it around. Okay.
Yeah, exactly. They use like deep space network. I think one of them is in California, maybe. I cannot really remember.
That's okay. And I just want to remind everybody, if you have any questions, please put them in the Q&A box at the bottom. So how did you, Yaolan, identify the stars, or have you identified the baby stars that you want to investigate?
Yeah, we have. We actually identified, because we have used other telescopes to look at the same source before and different wavelengths, and that's why we know what's their chemical composition in the gas, so that we want to learn from the ice. But in general, people have used like ground-based telescopes looking to like near-infrared wavelengths or Spitzer, and there's also a European-led Herschel Space Observatory that I think it is alive in maybe 2005 to 2010, about 6 years lifespan. They give us a lot of maps of those sources, so over time we kind of know where the infrared sources is, and there's a lot of radio telescope follow up, so we kind of understand the coal dust distribution really well. We understand the molecular gas composition really well, but what we don't know so far is what's the ice underneath those gas dusty cloud.
Okay. Let's see. I think I've got another question coming. Will you be able to detect planets orbiting these young stars while you are analyzing the ice?
Oh, I don't know. That we will get imaging at the same time for those sources. Yeah, I don't know. It will be great with the CME. You'll probably see me in headlines somewhere if we end up seeing them. That would be a great discovery. Because the thing that we really don't know is, or a lot of things that we don't know what to expect is Gemflip is so much more sensitive than, say, Spitzer, which is a previous telescope
Mhm.
that is observing the same wavelengths. So it's about 100 times more sensitive than Spitzer. So there's when we are preparing our programs, we have a lot of like, oh, whether we will see in these nearby really faint things we have seen other places, and a lot of them is like we don't know because we never be able to get even close to that order of magnitude of sensitivity before. So a lot of parameter space is really just on four. So will be great if we see any. It will be fine if we don't see any. We're still learning a lot about its surrounding materials.
Mhm. Let's see. Do other countries have space telescopes? Are there other space telescopes besides the one you've mentioned out there?
Yeah, there's so I think James Webb kind of fall into the category of so-called flagship telescope that takes 20 years to build, cost a decent amount of money. But yeah, European Space Agency have their telescopes. There's some missions like more dedicated to specific science. I think the most famous one recently is like European Space Agency has a kind of satellite, like smaller telescopes called Gaia. So what it does is measuring the distance to basically millions of different stars in our galaxies, so that we can know kind of put together the structures of our galaxy via the distance to those stars. Japan has its own space agency as well. They've been putting out infrared telescope before this Akali, I think in the early 2000s. They were trying to put out X-ray telescope a few years back. There's some issues about that. I think they're preparing for a follow-up mission on that as well. Yeah, so there's all kinds of missions happening, even for even in the United States. There's also specialized mission to do all kinds of different science. I think in maybe next year or in recent years, there will be a mission called Sphere X. This also would do infrared, but like in a larger field, just kind of map entire universe, those kind of things.
Oh, wow.
So yeah, all kinds of missions happening.
Okay. And what is the telescope's expected lifespan? Has been given a lifespan?
Yeah, there. Yes. I might be wrong, but my impression is 5+5. So 5 will be like has to be last for 5 years, and the +5 is it should be good for another 5 years. So that's my impression. It will definitely last between 5 to 10 years. The cool thing for James Webb that's compared to different telescopes is it has some really tricky or dedicated cooling system that doesn't require you carry a lot of coolant into the space. Because one of the issues for European Herschel Space Observatory is that it's observing even redder lights, but it kind of out of emission because it kind of ran out of the cooling because the telescope get warm to do stuff.
Okay.
But the Webb has some mechanical like cooling system to solve this kind of issue. So in theory, it can last even longer than those 5+5 lifespan.
All right. Let's see if we have any other questions. Let's see. I don't know, we might have another question. So yeah, so the lunar eclipse is tonight.
Yes.
At 3:03 a.m.
Yes. If you want to see it, I would suggest you kind of maybe wake up around 2-ish. There's no need to watch the first like quarter. Just kind of boring. I'm tired.
Okay. Yeah. 3:03 a.m. I don't know how many takers we'll have on that. So, but will you be up for it? That's a question.
I probably won't. But, I know there's a professor in UVA at Murphy. He will be in our university observatory tonight in the morning. So if anyone wants to travel to Charlottesville, You'll be there.
He'll be there. Somebody will be there.
Yeah.
Okay. Well, I don't think, well, I'll give it a few more minutes, but I did want to share that if you are interested in actually watching the launch, you can register off of the NASA's event page for James Webb. There's you can link to the James Webb Space Telescope mission, and from there you can actually register to watch the launch. So I did that the other day, so it's very exciting because we've learned all about this tonight. So you want to watch it launch and go up into space on this huge rocket and watch it deploy. So I would encourage everybody to do that. Yeah, so I think unless there are any other questions, this is your last chance, community. Okay, well, thank you so much, Yaolan. This was wonderful. I appreciate you taking the time to talk a little bit about your research and then all about the James Webb Telescope and what it will show us and how scientists are going to be using this for hopefully the next 10 years to show us all sorts of new and interesting things. So
yeah, of course. This is fun. And I think I'm really happy to talk to anyone about James Webb.
Good. We like that. We may come back to you. So once it's launched, we'll wanna hear all about
it. Yeah. I can share my data with you guys whenever we have it.
Wonderful. Okay. Well, thank you so much. And thank you everybody for tuning in tonight. And we will we've been recording. So this will be up next week and you can see it again. All right. So I'm gonna say goodnight to everybody and happy Thanksgiving from
happy Thanksgiving.
That's right. Happy Thanksgiving, everybody. Have a good night.
See you guys.
Bye.